if the Poisson random variable, it's a discrete random variable. For example, number of customers that enter a bank in 1 hour. Okay, so number of customers that enter a bank. Obviously, this is a discrete number. So I show it by x. X is the Poisson random variable, which is number of customers entering the bank in 1 hour. So x has Poisson distribution. Okay, so let's assume that the first customer arrived here, the second customer came here, the third customers came here, fourth one came here. I'm just, it's a random thing, right? Let's assume that. So this is the first customer, second customer, third, fourth, fifth, and let's assume this is the sixth customer, and that's one example of what happens, for example, in 1 hour in a bank. So, and that we said has exponential Poisson distribution. The exponential random variable is looking at these times, the time between arrivals. So obviously, if the number of customers that enter a bank is variable, which means that at 1 hour we may get more customers, at 1 hour we may get less customers. So then the time between arrival of customers, then it's not fixed, it's variable, right? If the time between arrival of customers is fixed 10 minutes, then every hour exactly 6 customers would enter the bank. There is no variability here. Every hour, exactly 6 customers, the time between arrival is exactly 10 minutes. But when I say the number of customers that enter a bank is a random variable, that means, okay, on average, maybe 10 customers enters the bank, but next hour, maybe 2 customers enters the bank. Next hour, maybe 20 customers enter the bank. So the number of customers that enter the bank is random. So if that's the case, then the time between arrival of customers is random too, is not fixed. Okay, and this time between arrival of customers is the random variable that has exponential distribution. So if I call it as random variable y, that's the time between consecutive arrival of customers. And this random variable is the one that has exponential distribution. And obviously, since it shows the time between arrival of consecutive customers, like this time, these are all variables that have exponential distribution, and obviously, since they are variable, they're different from each other. It's not that the time between arrival of 2 consecutive customers is exactly this amount of time. It varies between every 2 consecutive customers. But since it's a measure of time, it's obviously a continuous random variable. Okay, and that's why I told you guys when I was telling you that we are going to learn about Poisson and exponential random variable, I said there is a relation between those two, and that's why we put them in module 4, so that you can see the relation between Poisson and exponential random variable. So for every Poisson random variable, there is always a corresponding exponential random variable. Poisson random variable is discrete, is looking at number of things, number of events that happen in a time frame, number of customers that enter a bank, number of cracks in a mile of highway, a number of calls that are made to a call center. However, the exponential random variable, the exponential counterpart, looks at the time between those events, the time between arrival of customers to a bank, the time between arrival of consecutive calls to a call center, the time between, the distance between cracks in a mile of a highway, and so forth. So that's the continuous exponential random variable corresponding to each Poisson random variable. And to be able to calculate both of them, no matter if it's no matter if you want to answer the question related to the Poisson random variable, or if it's a question related to the exponential counterpart, to answer any one of them, what I need to know is lambda, which is average number of events or things that happen in a unit of time. The same lambda that we talked about in previous sessions. So the same lambda that is used in the Poisson formula, and that's the same number, that's the same lambda that is used in the exponential formula. Okay, so in the Poisson, we say probability that x equals to some number, which means, for example, number of events, number of customers that enter the bank in 1 hour is 5. It's e to the power of minus lambda, lambda to the power of x over x factorial, and then on the corresponding exponential, if I say the probability that the time till the next customer enters the bank is less than some specific value y, it's lambda e to the power of obviously it's integral from 0 to y, lambda e to the power of minus lambda y dy. Okay, so it's the same lambda that is used in any one of them. So to be able to answer a question related to a Poisson random variable or an exponential random variable, all I need to know is this average number of events or calls or customers or cracks or whatever in that unit of time or that unit of space. Okay, so let's look at the practice problems that I posted in previous session. The last question was exponential random variable. Okay, it says web crawlers need to estimate the frequency of changes to website to maintain a current index of web searchers. So the changes are made to the website and they are looking at frequency of these changes, like how frequent these changes happens, how many changes per hour, and so forth. So let's say if this is the time dimension, and let's say this is 0. So this is when the first change happens in the website. This is when the second change happens in the website. The third change happens in the website. The fourth change, the fifth change, I don't know, the sixth change, the seventh change, and so forth. This is the phenomena. I have the time axis, and I'm looking at when the first change happened, second change, third change, fourth change, and so forth happen in the website. Can someone tell me, in this phenomena that we just explained, if you want to define random variable x, which has Poisson distribution, the discrete random variable x that has Poisson distribution, can you tell me what is the definition of that random variable? Just give me in one sentence. What would be that discrete random variable that can capture what happens in this phenomenon?
It would be the time until the next change.
Poisson. Discrete. When you say time till next change, is it discrete? Time is always a continuous random variable, right? Can you look at this phenomena from a different perspective? Still, we are looking at changes that happen in the website, but as opposed to looking at time between changes, how else you can look at this? How about number of changes? Number of changes in a specific time. But if I define x as number of changes in the website in an hour, is this random variable fixed? Is this a fixed value? If I look at number of changes in the website in an hour, can I say that always there is 10 changes in this website in each hour? Can I say that?
12 the next hour.
That's correct. So if I'm looking at number of changes in a website, and if I call that to be a variable, then I can say that, yes, for the number of changes in the website, I'm going to report an average number of changes in a website. Then that can be anything. Let's assume that's 10. That means on average in each hour, in an hour. That means on average, in an hour, there are 10 changes in the website, but it's average. So next hour, this may be 2 changes. Next hour, this may be 10 changes. Next hour, it may be 20 changes. On average, it's 10, but I don't know exactly what is the value of number of changes that is going to happen in the next hour. I know average is 10, it should be around 10, but I don't know exactly what that value is going to be. Okay, so then one way to look at this whole phenomena is by looking at number of changes that can happen in the website in an hour, and this is obviously a variable. And since I'm looking at number of changes, this is definitely discrete. 0 change, 1 change, 2 changes, 3 changes, all the way to infinity. This is definitely discrete, and this random variable has Poisson distribution. Okay, and the parameter that I need, lambda, that I need to be able to answer any questions related to this random variable is average number of changes in the website in an hour, and I already have it, and that's 10. Okay, so now I want you to tell me what would be the next, what would be the other way to look at this phenomenon. You guys actually answered my question initially.
You could also look at the problem as the time in days until the
Exactly. So now I also can look at the time between these changes. Okay, so then that I will consider that as y. So then y would be time between consecutive changes in a website. And obviously, since it's time, it's continuous random variable, and that's it's a continuous random variable, and that's what I'm going to call as exponential random variable. Okay, that's why I say Poisson and exponential are related to each other, because basically for every Poisson random variable there is a corresponding exponential random variable, and for every exponential random variable there is a corresponding Poisson random variable. You can always look at either as number of events that happens in a time frame or the time between these consecutive events. Okay, a simple example, I can either tell you 6 customers per hour arrive to a bank, exactly 6 customers per hour arrive to a bank, or I can tell you the inter-arrival time between consecutive customers is 10 minutes, then you make the same conclusion. If I tell you the time between arrival of 2 consecutive customers in a bank is exactly 10 minutes, you immediately can conclude that 6 customers entered the bank in an hour, right? So 6 customers entered the bank in an hour. I'm talking about this Poisson aspect of it, 6 customers per hour, or I'm telling you it takes 10 minutes between arrival of every 2 consecutive customers to the bank. So it's more like an exponential aspect of it, the time between arrivals. But both of them are giving you the same information. Either 6 customers arrives to a bank in an hour, or the inter-arrival time of consecutive customers is 10 minutes. They are giving you the same information in terms of frequency or how fast these customers come to the bank. Okay, so they are pretty much the same. So now let's let's go back to the problem. Okay, now it says that we need to estimate the frequency of changes to a website to maintain a current index for the web searchers. Assume that the changes to a website follow a Poisson process with a mean of 6 days. The sentence I would say, actually, I would correct it. I would say, assume the time between consecutive changes to a website is 6 days, something like that. So let me write that here. Okay. Assume that the time between consecutive changes to a website is 6 days. Okay, so again, this is the time access. These are when the changes happens to the website. The time between consecutive changes to the website, the average of these is 6 days. Okay, so our random variable x, I mean, if I here, or I actually am going to, oops, call y, because in previous we just called it y. So y, which is the time between consecutive changes to the website, then average of y or mean of y is 6 days. Okay, that's what we can read from problem statement. Let's variable x denote, I mean, let's variable y denote the time till next change. Okay, so the time between consecutive changes, or the time till next change, is our random variable which has exponential distribution. What is the probability that the next change occurs in less than 4.5 days? The probability that the time till next change, which we show with random variable y, is less than 4.5 days. Okay, and we know the formula from exponential random variable, so that is 0 to 4.5 days, e to the power of lambda, e to the power of minus lambda x dx. And then this was calculated for you guys in the videos you have. This is 1 minus e to the power of minus lambda x. Okay. So then all you need to do here is to find the value of lambda, to put it in this formula. Okay, and lambda, as we just mentioned here, lambda basically is average number of searches that can happen in a day. Okay, so I want you guys to pay attention to this. If the question says, what is the probability that the time till next change is less than 4.5 days? Then your lambda also should show average number of searches that can happen in the same time frame, days. Okay. If question says, what is the probability that the time till next change, I don't know, is less than, I'm just making this up, is less than 30 minutes, for example, then your lambda should show also average number of changes that can happen in minutes. So that's the only thing that you have to take into account when you answer any question related to the exponential random variable. If the question is asking, what if the probability that this time is less than 4.5 days, then your lambda also should look at the average number of things that can happen, or average number of searches that can happen in days. Okay, these have to have the same time frame. Okay. Now, then the question is that how can I find lambda? One piece of information that we have is actually here. We know that expected value of y, average number of days till a change happens is 6 days. Can you tell me how I can use this to find the value of lambda? Remember from the formula in the videos, average of this exponential random variable is 1 over lambda. That's the formula always. For exponential random variable, average is 1 over lambda. Okay, and here lambda is 6. Sorry, the average is 6, so this is equal to 6. So if I have this, then I can say that lambda is 1 over 6, which is basically the date, the unit is 1 over 6 of a change per day. So this part basically says the time, average time till the next event is 6 days. So the time till next change is 6 days. So basically 6 days for a change. So the time till next change is 6 days. So it's 6 days for a change. And here when I look at expected value of y, or average time till next change, and I say, okay, it's 1 over lambda, then this unit will be inverse too. So so this is basically 6, the same unit that I wrote here. 6 days for each change. So here, when I'm finding the value of lambda, I say, okay, it's 1 over 6. I remember the unit for 6 was day over days per change. So when the 6 is inverse, then the unit is inverse too. So then the unit for lambda, as we expect, is 1/6 of a change per day. Lambda is always average number of things that can happen per unit of time in a day, in a minute, or anything. So now that I have lambda, then all I need to do is to put the lambda in this formula. So probability of y less than 4.5. Okay. And whatever that number is that's going to be your probability. Okay. So the next part B says, what is the probability that time till next change is greater than 9.5 days? The probability that time till next change, y, is greater than 9.5 days. So if I want to write this, I can write this as 1 minus probability of y less than 9.5 days. And I can write it as 1 minus, then I know how to calculate this, like what we just calculated on the top. The formula for that is 1 minus e to the power of minus lambda x. So that's e to the power of minus lambda x. When we simplify, these ones cancel each other. And lambda, we just calculated, that is 1 over 6, and x is 9.5. Okay. What is it? Part C? What is the time of the next change that is exceeded with the probability of 90%? So basically it says, what would be this? what would be this time that I can say that with probability of 90%, this random variable which captures the time till the next change is going to exceed that. So I can say with 90% of the time till next change exceeds this value. What is that lowercase y number? That's what we want to find. What is the time till next change such that we always can exceed it with probability of 90%? That's what it means. So then I can write this as 1 minus probability of y less than lowercase y, that's 0.9, or probability of y less than lowercase y equals to 0.1. And again here, this is the probability that we know, e1 minus e to the power of minus lambda y. And lambda is 1 over 6. And we can just solve this and find the value of y to know, to know what is the value of y, such that we can say that 90% of the time, 90% of the times, the time till next change exceeds this value, whatever lowercase y is. So we are trying to find the lowercase value of y to say that 90% of the time till next change happens in the website is going to exceed that value. And then the last question, part D, says, what is the probability that the next change in the website occurs in less than 12 and a half days from now? So the probability that the next change happen in 12 and a half days from now, given that, the change has not occurred in the past 3 days. Okay, so if we know that no change has happened in the past 3 days, what is the chance that it takes another 12 and a half days till the next change happens? So that's that takes us back to the memoryless property of the exponential random variable, which was your last video. Which basically says knowledge of the past has nothing to do with the probabilities of things happening in the future. The fact that I know it's 3 days till the next event happened has nothing to do with the probability of what if the chance that it takes another 12 and a half days till the next event happens. So I can just answer this question as if I don't know if it's already 3 days that something has happened or has not happened. So this is equivalent to probability that next change happens in 12 and a half days. Or probability that this random variable is less than 12 and a half days. We want it to happen in the next 12 and a half days. So it should happen somewhere in the next 12 and a half days. So we want to find the probability that y is less than 12 and a half, and that's 1 minus e to the power of minus lambda y, b1 minus e to the power of minus lambda, which is 6, and y is 12 and a half. Okay. Now, this is question 3. Is there any question regarding the problem number 3 so far? Okay. So I want you guys to look at problem number 1. It says number of telephone calls arrive at the call center has Poisson distribution, is a Poisson random variable. Number of calls that arrive at the call center in an hour has Poisson distribution. Number of calls obviously is a discrete random variable and has Poisson distribution. Number of calls that arrive to a call center in each hour. So I'm going to call it, so this is question 1. So I'm going to call it X, and it's number of calls that arrive to a call center in an hour. Can you tell me what is distribution of this random variable?
It's Poisson.
It is Poisson because
It's a discrete, it's a number.
it's number of calls, it's discrete in a time unit, in a dimension of space or distance and so forth, or time. Number of calls in an hour. Can you tell me the corresponding exponential, I can define here?
The average time between calls.
Or just the time between consecutive calls that are made to a call center. Okay, so this would be the corresponding exponential. This x will be the corresponding Poisson random variable. So I can give you questions and say, what is the probability that number of calls that are made to a call center in the next hour is exactly 5, that's part A of question 1. What is the probability that we have 3 or fewer calls in the next hour? Those are all Poisson. You have to use the Poisson formula to answer those questions like we did in previous session. Or I can say, what is the probability that the time till the next call arrives is less than 20 minutes? Or let's say less than 2 hours. Let's keep the unit as time. Okay. So, or I can give you questions like, what is the probability that the time till the next call arrives is greater than 1 hour and a half? Okay. So, if I ask you questions like this, then you need to find lambda, and all you have to care about when you find lambda, and lambda is going to be average number of calls in which unit of time? Lambda that you need to be able to answer these 2 questions is average number of calls in how long?
An hour.
In an hour. All that matters is that it's in an hour. Okay, and the question tells you that this center receives 10 calls in an hour. Okay, perfect. You have the lambda, put it in the formula, find the answer to these questions. Now, let's assume I asked you, what is probability that the time till next minute, the time till next call is greater than 30 minutes? You still need to find lambda to know lambda to be able to answer the questions. And lambda, again, is average number of calls. And what is the unit of time here? We have to find average number of calls in how long?
For here, it's minutes.
It should be minutes. Pay attention to that. If the question asks you average the probability that y is greater than 30 minutes, then your lambda also should count average number of calls that you can receive in minutes. They have to be the same. If here is hour, your lambda is in hour too. If here is in minute, your lambda is in minute too. If you want to stick to your lambda in hour, if you still want to use this lambda in hour, the one that we already have, which gives us the number of calls in hour, if you still want to stick to this, then change this time to hour too. That's fine. Then if I want to change that time to hour, then I'm going to rewrite this as probability of y greater than, if I want to change that to hour instead of 30 minutes, I have to write what? 30 minutes is how many hours?
0.5.
0.5 hour, exactly. I can write this, the same question, I can write it in this form, and then I'm good to use the same lambda 10 calls per hour if I want to. That's fine too. So you can answer these questions in two ways. Either keep it as this, your question is that what is the probability that the time till next event is or next call is greater than 30 minutes? That's fine. Just make sure your lambda shows average number of calls in minutes. That's fine. Or if you still want to use your lambda, which shows number of calls per hour, make sure to change your question to show it based on whatever you need in hour. The probability that the time till next call is greater than half an hour, not 30 minutes. And that's perfectly fine. You can answer the question using any one of them and you have the same answer. Okay. That's all you have to pay attention to. Look at what question wants from you and make sure to get your lambda in the same time unit. The rest is just plugging in the formula and finding the answer. For example, in question 2, it says number of cracks in a section of highway have Poisson distribution. Yeah. Okay, so then in question 2, it says number of cracks. We are looking at number of cracks in a mile of highway. First of all, tell me, what is this random variable? Number of cracks in a mile of highway.
Poisson.
It's Poisson because it's number of things in a measure of distance here. It's not time, it's a measure of distance. So I'm going to call this x, and this x has Poisson random variable. Is Poisson random variable is discrete? Perfect. Can you tell me what is the corresponding exponential?
Distance between the cracks.
Exactly. The corresponding exponential will be distance. between the cracks. Okay, that is continuous. Obviously, it's distance, and that's the random variable that has exponential distribution. And it tells us that the problem says that on average we have a mean of average of 2 cracks per mile. So your lambda is 2 cracks per mile. So if I tell you what is the probability that the distance till the next crack is less than, I don't know, half a mile, then 1 minus e to the power of minus lambda x. Your x is obviously 0.5, but all is good because your x is in mile, your lambda is in mile too, cracks per mile. So then this is going to be 1 minus e to the power of minus 2 multiplied by 5. Okay. And that's all you need to be able to do the calculations. So for every Poisson random variable that counts number of things and is discrete, there is a corresponding exponential which counts the time between those things or the distance between those things. Okay? And both of them need lambda to be able to answer any question, no matter if it's exponential or Poisson. And lambda is average number of things that can happen in a time unit or in a unit of distance or a unit of space, whatever that dimension is. And all you have to pay attention to when you answer questions related to the exponential version of the problem is that in the exponential, if it asks you, what is the probability that, for example, the distance till next crack is less than this amount of mile, your lambda also should be in terms of cracks per mile. If the question asks you, what is the probability that the time till next call is greater than half an hour, then your lambda should also be in terms of average number of calls in an hour, the same time unit. If I ask you what is the probability that the time till next call is greater than 30 minutes, then your lambda also should be average, based on average number of calls per minute. If that's not the case, just do the transformation. If you have the call per minute, call per hours, okay, transform it to call per minutes and just put that lambda. Or like what we did here, change the question to the unit of lambda. If the lambda is per hour, change the question to per hour thing. See which one is easier. I mean, for here, 30 minutes to half an hour was an easy transformation, but sometimes it may not be as easy. So see which one is easier. All that matters is that the unit of time in the question and the unit of time or dimension or distance and whatever in lambda should be the same.